The third talk is about common sense mining.
Hi, so today we're going to be talking about mining common sense knowledge from pre-trained models. My name's Josh Feldman, this is Joe Davison, and we worked on this with Sasha Rush. So the task we're going to be looking at today is common sense knowledge-based completion. And that involves when you're given a set of tuples, and the tuples contain common sense knowledge, so a head relation tail expressing common sense facts. And the goal is to learn a model that assigns a score to those tuples which correlate with whether the tuple is true or not. So as an example, we have rook is a chess piece. That's true, common knowledge. And then that's a positive example. And then we have rook is a tool, which is not true. And you'd want to assign a low score to that. So up until recently, most approaches to this problem have taken a supervised approach. So you train a model on a bunch of tuples and then apply it to some sort of test set. Jastrzębski et al. Found that that approach tends to lead to overfitting to the training data. And then when you apply the model to tuples that are very different from the data that you trained on, performance drops pretty quickly. And so we're trying to address that issue by using BERT. So in theory, you could use BERT to get around this problem because BERT is trained on a huge amount of text, and so it shouldn't be biased towards any training set of tuples. But and then hopefully it would then generalize to new data a little bit better. So concretely, what we're trying to do is we're taking the tuples and converting them to sentences, and then using BERT to score those sentences, and that score relating to whether the original tuple is true or false. So this is part of a growing body of literature about using language models to do common sense tasks. So you can break it down into sort of three categories. One group of papers are about using language models and variants of them to perform tasks that require common sense. Another section is using language models to do supervised common sense knowledge-based completion. So you train a model on tuples. You train a language model on tuples and then apply it to unseen data. And then there's the final category, which is what this work falls under, which is unsupervised common sense knowledge-based completion, where you just take a language model and you don't train it on a data set of tuples. So to break down our approach, we sort of have two submodels. One is generating text from tuples, and then the next part is using BERT to then score those sentences. So you can see that laid out right there. So I'm going to go into the sentence generation part first. So the way it works is we tried a couple different methods. This one worked best, but if you want other details, you can look in the paper. So what you do is you take a tuple, and then what we did is we wrote a bunch of templates for each relation. So here you have 2 templates for the relation capable of. So that gives 2 candidate sentences, but you can see that these sentences aren't grammatically correct, and so you then apply grammars to those sentences, and then you get a big list of candidate sentences, and with the hope that one of them is correct. And then finally, you take those list of sentences and score them with a language model. Different from BERT, we use GPT-2 for this, and the most probable sentence was the one we used. So here you can see that after doing all this, you end up with the sentence, a musician can play a musical instrument, which is good because it's grammatically correct and it represents the meaning of the original tuple.
Yeah, so now that we have a way of taking these tuples and generating high fidelity sentences from them, we want a way to get scores out of BERT after we put it into the model that hopefully corresponds to the truthfulness or the validity of the sentences in some way. So the metric we use for this is pointwise mutual information. So BERT has this really nice property where when you put a sentence into the model, you can mask any combination of words, and those words will be excluded from the context of the sentence. So the way we use this is that we can calculate the conditional and the marginal probabilities here with SOAP, which is the head relation in this sentence, being masked and unmasked. So to make this a little clearer, we have the sentence, something you are likely to find in the shower is soap. That's the sentence that we're putting into BERT. And we are measuring the probability here of the tail relation being equal to shower. So we start with this, which corresponds to the marginal probability. And then after we unmask the head and reveal that that is soap, we're measuring how that changes the probability of T being head. When you subtract those two values out, that gives you the pointwise mutual information, which is a really nice intuitive metric that tells you something about the relationship between these two entities, given the relation that you're dealing with. And we found that this worked really well. However, we also found that in some cases, it undervalued the parts of the sentence that were key here, that we're interested in modeling. So to that end, we introduced a hyperparameter for a form of the weighted PMI. And what we have here is the lambda value on the conditional term that simply allows us to tune this hyperparameter and make sure that we're not undervaluing the context of the sentence. So I also want to mention that this is for the case of single word entities where you can easily look up the probability in BERT. In the paper, we also describe an extension for entities that are arbitrarily long. All right, so now we'll talk briefly about the experiments that we do. The first is on a common sense knowledge base known as ConceptNet. In 2016, a paper by Lee et al. Selected 100,000 of the most confident tuples from ConceptNet, and they then permuted some of the values to also create incorrect tuples that don't actually correspond to true knowledge. And they, from this, they created a train set and a test set, which became sort of the standard for the common sense knowledge base completion. So in this problem, we want to emphasize again that we're comparing our method, which was never explicitly trained on the ConceptNet training set, with methods that were explicitly trained on the training set. We only evaluate on the test set. Okay, and then the second task, with the goal of evaluating the generalizability after you've trained on ConceptNet, is on Wikipedia text, where candidate tuples are evaluated or extracted from Wikipedia using NER patterns. And then the task is to take the 100 highest scoring of these candidate tuples according to your model and qualitatively evaluate them on a scale from 0 to 5 so that you get a sense of how high quality the tuples that your model identified really are. So like I said, previous work used this task. They trained their models on the training set from ConceptNet, and then they evaluated on Wikipedia as an evaluation of generalizability to unseen knowledge. So for the results for ConceptNet, you can see in this table, these are a few of our ablations for the different sentence generation methods. Coherency ranking is the one that Josh described for generating sentences. And you can see that despite our model never being trained explicitly on the ConceptNet training set, it begins to near the performance of some of these models that were explicitly trained on it. And then when evaluating the generalizability on Wikipedia, our model outperforms the previous approaches, which supports our intuition that BERT and the intrinsic and the breadth of knowledge that BERT saw in its training corpus allowed it to generalize better than methods that were explicitly trained only on one knowledge base. So in conclusion, we found that with this method, we can mine common sense knowledge from pre-trained BERT, relying on the general knowledge that it was able to capture from the general training corpus that it saw. And though our approach performs worse on a held-out test set on ConceptNet, it performs better than those supervised methods when generalizing to novel data. And lastly, we want to emphasize that this may not explicitly mean that BERT has common sense in some intrinsic sense, but there is a sense to which BERT has some sort of latent knowledge base. Although the extent to which, first of all, it's somewhat non-trivial to access whatever latent knowledge is there, and second, it's unclear to what degree that knowledge base has high coverage and is high quality. So for future work, we are interested in finding ways that this approach may or may not be applicable to knowledge that is not defined as common sense knowledge, but is more knowledge in a broader sense. And we are also interested in other ways of evaluating the generalizability of CKBC, of common sense knowledge base completion, given the qualitative component that was necessary for our Wikipedia generalizability evaluations. Thank you.
Questions?
Thank you for your presentation. I'm interested in the task 1. You said by permutation the tuples to get wrong tuples, but by chance they may be correct, right?
I'm sorry, I didn't quite follow. Can you say that again?
I mean, in task 1, you try to generate the wrong samples by permutating the tuples, but by chance you can get correct ones, right?
Yes, yeah, absolutely. There's a chance that those wrong examples will have a few that are correct. It's under the assumption that the vast majority of them will be incorrect.
Okay, thank you.
Yeah.
Other questions? Oh, yeah.
Hello. Hey. Yes, if I understand correctly, so you're using the language model probability difference to treat it as some sort of confidence score about the common sense between those pair of entities.
Yes.
Have you considered there may be some variations, like deviations on the confidence score between different type of entity? Do you consider any type of normalization on that score so you can have like a fixed thresholding to do the binary classification?
Sorry, what's the different, what do you mean by the different types of entities?
So maybe different type of entity, the difference between the probability has some variance. Some maybe have a larger gap, some have a smaller gap. So if I understand correctly, you're using a fixed thresholding to do the binary classification, whether that's common sense or not. But maybe that threshold should has different values for different type of entity.
Yeah, that's an interesting point. That's not something we've looked at explicitly.
Okay.
I have one question. So how your approach works for long tail triples or low frequency triples? Did you observe it still works very well for those types of data?
So you're asking whether this works for the long tail of... Yeah, so we didn't investigate anything quantitatively about that, like distinguishing between different types of tuples, but just from reviewing the high probability or like the tuples on the Wikipedia task that were likely to be common sense, a lot of them were very sort of obscure facts that we had to look up. So that means that it's definitely verging beyond what common sense knowledge would be and getting into like factual knowledge from the Wikipedia data that it was trained on. This kind of connects back to the last question where you can imagine that our method of scoring tuples will overemphasize rare words. And so having some sort of normalization might either prevent you from getting that, or if that's what you're looking for, maybe a different way of normalizing would bias towards those types of facts. So it's interesting. But
Okay, thank you. Okay, let's thank the speaker again. Thank you.